We begin this section with a discussion of a new operation on vectors, and then we'll talk about how that operation is useful. The operation is called dot product, and we make the calculation like this. Suppose vector u in component form is 5, 2, and v in component form is 3, 4. The dot product of u and v is found by multiplying items that are in corresponding positions and adding those products. So it's 5 times 3 plus 2 times 4. And collecting here, we find the dot product of u and v to be 23. Here's how dot product is used. It is used, one use of it is to find the angle between two vectors. The angle between two vectors. Now here's what I'm talking about. If we have the same two vectors we talked about a moment ago, and I put them onto a coordinate plane, and if I position them so that their initial points are both at the origin, then they would look like this. Here's u and here's v. Now I know this is u because, let's see, the components are, let's see, horizontal and vertical, so it's 5, 2, you see, and then v would be 3, 4. Okay. Now it isn't necessarily the case that we have to be talking about the vectors positioned at the origin. They can be positioned just about anywhere on the coordinate plane, and we can still talk about the angle between them, or the angle relative to those two vectors. And for example, if we're thinking about the vectors over here, and this would be u then and that would be v, then the angle, you see, between them, the angle relative to those two, would be the angle we find by extending them a bit, and this then is the same angle theta that we're looking at up here. So we're trying to find the size of angle theta. Now, you know from the previous section that one way to do this would be to find the angle associated with the vector v and find the angle associated with vector u, and then just take the difference between those two. And that wouldn't be very difficult in a case like this. But perhaps it's a little more direct, and we have a lot of other uses for the idea of dot product. Here's how dot product is used in this process. It turns out that the cosine of that angle between the vectors is the dot product of the two vectors divided by the product of their magnitudes. The product of their magnitudes. So let's see, the dot product of u and v, we calculated it before. It's 5 times 3 plus 2 times 4. And remember where that comes from. It's 5 times 3 plus 2 times 4, all right, to give this numerator. And then for the denominator, the magnitude of u means the square root of the sum of the squares of the components. There's a mouthful. But for u, it's the sum of the squares of 5 and 2 under a radical. So it's the square root of 5 squared and 2 squared. And for the magnitude of v, same idea, sum of the squares of the magnitudes. The magnitude was 3, 4, so it's the square root of 3 squared plus 4 squared. And then simplifying a bit, we find our fraction to be 23 over the square root of 29 times the square root of 25. Square root of 25 is 5, so we get this fraction. Now, if the cosine of theta is equal to this fraction, then theta is the inverse cosine of the fraction, and we find theta then to be 31 degrees. So this angle theta then is 31 degrees. And the angle, the relative angle between the vectors positioned like this would also, of course, be 31 degrees approximately. Here's one of the nuances involved with finding the angle between vectors. Suppose the vectors are 4, 6, and 3, negative 2. And we want to use our formula here to find the angle between them, and we go about the business of making the calculation. Let's see, the dot product of u and v in this case would be 4 times 3 plus 6 times negative 2. And in the denominator, it's the, let's see, for the magnitude of u, it's the square root of 4 squared plus 6 squared. And for the magnitude of v, it's the square root of 3 squared and negative 2 squared. All right, and then, let's see, in the numerator we have 12, and 6 times negative 2, that's negative 12. 12 with negative 12, oh, that's 0. And in the denominator we have the square root of 52 and the square root of 13 for the factors, but it really doesn't make too much difference in the denominator because the numerator became 0. And when the numerator of a fraction is 0, the whole fraction becomes 0. And if the cosine of theta is 0, then the inverse cosine of 0, the inverse cosine of 0 turns out to be 90 degrees. That is, the angle whose cosine is 0 is a 90-degree angle. So the two vectors then are relatively perpendicular. They're perpendicular to one another. Now if we actually position these two vectors at the origin of our coordinate plane, we can kind of see it pretty easily. We have a situation where, let's see, we have u is 4, 6. That's about right here. And v is 3, -2. About right here. And that is a 90-degree angle. Now, if they're positioned in other places on the coordinate plane, they're still relatively perpendicular. That is, if this vector is up here and this one is, over here, then by extending them in both directions, we can imagine that they are perpendicular. Now, this relative perpendicularity idea has a special name in trigonometry. It's called orthogonal. The two vectors are said to be orthogonal if the angle between them is 90 degrees. Now let's review the idea. We start out with this formula for calculating the angle between the two vectors, but if we find that the dot product is 0, that's just the numerator up there, then if the numerator turns out to be 0, then the whole fraction is 0, and the cosine of theta then is 0, theta then is 90 degrees, and the two vectors are said to be orthogonal. Okay. Couple of other interesting situations can occur, rather special situations, I guess. If u is this vector and v is this vector, and we go into our formula and make the appropriate calculation for dot product and magnitudes in the denominator, we get this. And then when we resolve the situation in numerator and denominator, it turns out we have the same number in numerator and denominator, so the fraction becomes 1. Now, if the cosine of theta is equal to 1, you see, imagine the graph if you want to, put it into your calculator if you'd like to. You find that theta is 0 degrees. Now, if we have a theta of 0 degrees, if those two vectors are positioned with their initial points at the origin, then they're kind of lying right on top of one another. And the important thing, too, is that they are pointing in the same direction. So when we have a 0 degree for that angle between them, u and v then are parallel, and they're going in the same direction. Now I say parallel here. I mentioned a moment ago that they're right on top of one another, but that's only if they're positioned with initial points at the origin. If they don't have initial points at the origin, then one of them could be up here, and the other could be down here. But the idea is, and I'm just making one longer than the other, I'm not trying to make these correct to the figures that are up there, but I'm trying to make these go in the same direction, you see, and that's the idea. So they're parallel and they're going in the same direction. Now, imagine what would happen if this value were -1. See, if this value were -1, then the inverse cosine of -1 is 180 degrees. So if we had a -1 here, then we'd have a theta of 180 degrees. That's the angle between them. And so they would be going in opposite directions, you see, and so they would be parallel, but going in opposite directions. All right, to summarize, it's this idea. If the cosine of theta is 1, then theta is 0 degrees, and the vectors are parallel, but they're going in the same direction. If the cosine of theta is -1, then theta is 180 degrees. The vectors are parallel, but they're going in opposite directions. Now, there's one other thing about this idea of going in the same direction, going in opposite directions, particularly going in the same direction. Gee, if they're going in the same direction, then it turns out that the two vectors can be expressed as a scalar multiple of the other. I mean, look at u and v here. I've got 4 and 6. Now, 6 is just 1.5 times 4, and 21 is 1.5 times 14. You see, so I can write one of these as a scalar multiple of the other. And I think the easy way to do it is like this. I can say that v is 1.5 times u, because understand that v then is 1.5 times the u of 4, 14. And we know that 1.5 times each of these gives a v of 6 621 as expected. But it's an interesting notion that when we have this idea of parallel and same direction, we can rewrite the vectors one as a scalar multiple of the other. I want to remind you of the alternate notation that we use for vectors. Remember, if u is 3, 5, then we can use this more algebraic kind of form of 3i plus 5j, introducing the I and j into the problem. We can kind of verify that these are indeed the same if we think of I as the unit horizontal component vector 1, 0, and j is the unit vertical component vector 0, 1, and multiplying here we would get 3, 0, and here 0, 5, and this is a horizontal of 3 and a vertical of 5, so we get what we started with as expected. Anyway, we can use this kind of form, this ij form, in making our calculations about the angle between a couple of vectors. If u is I minus 6j and v is 2i minus 12j, then we apply our formula in the way that we did before. It's the dot product over the product of magnitudes. And for dot product now, it's understood 1 times 2, and then plus negative 6 times negative 12. And in the denominator, for the magnitude of u, it's the square root of the sum of the squares of the components, and the components are 1 and negative 6. So it's 1 squared plus negative 6 squared under the radical. And for the magnitude of v, it's these components squared, so it's 2 squared with negative 12 squared under the radical. And when we make the calculation, we find that we have 74 over what ends up being 74, and that is 1. And we know that when the cosine of theta is equal to 1, then theta is 0 degrees, and the vectors are parallel, and they're going in the same direction. Now, under this circumstance, remember we talked about the idea that one of them can be written as a scalar multiple of the other. And it's pretty easy to see that we can see that v is just double u. Just double these ideas right here, double I and double the negative 6j, and we get 2i minus 12j. So no surprise for the outcome here. Now, I want to talk to you about another formula that we're going to use from time to time. And to introduce the formula, though, we'll talk about some things that we have considered in the past. Suppose we have a vector u that's described by an object traveling at 50 feet per second at an angle of 60 degrees. Now, we know that there are a number of ways of describing this in horizontal and vertical component form. And probably the easiest way to do it when given information like this is to use the r cosine theta, r sine theta idea. Now, r is the magnitude, and that's 50 here, and theta is the angle of 60 degrees. So it's 50 cosine 60 degrees, 50 sine 60 degrees. Cosine of 60 degrees is 1/2. The sine of 60 degrees is this fraction. And let's see, half of 50 is 25, and with the cancellation here, this becomes 25 root 3. So with this information, we know that this object that was projected at 50 feet per second on an angle of 60 degrees is really traveling 25 feet per second horizontally and 25 root 3 feet per second vertically. So we have an idea of how fast it's traveling horizontally and vertically. But suppose we don't care about those things. Suppose we care more about how fast it's traveling, not horizontally and vertically, but maybe on a different angle, on an angle of, let's say, 20 degrees. How fast is it traveling on that angle? Well, it turns out that we can project this vector u onto a vector that is along that 20-degree angle. Consider this. We want to know how fast the object is traveling relative to an angle of 20 degrees. Here's what we know about the problem. Here's our vector u, and it's traveling at 50 feet per second along this angle of 60 degrees. All right, we know from our calculation over here that it's traveling horizontally at 25 feet per second, and it's traveling vertically at 25 root 3 feet per second. But that's not what we really want to know. What we really want to know is how fast that rascal is traveling at an angle of, say, 20 degrees for our discussion. So, how fast is it traveling in this direction? That's what we're asking ourselves. So what we want to do is project this vector onto that line or that vector. You see, and again, we'll have a magnitude. The direction is, we know, to be 20 degrees here. So that's what we're aiming to do. Now, let's understand that this vector, which I'll call V here for discussion, can be described in a number of ways. I mean, since we know the angle is 20 degrees, we could describe this as a unit vector, in unit vector form of, now remember, r cosine theta, r sine theta. Well, r is 1 here for unit vector. So it'd be 1 cosine 20 degrees, 1 sine 20 degrees. Now realize that cosine 20 degrees is just a number in the calculator, and sine 20 degrees is a number in the calculator. So it's just the combination of those two numbers that gives us the idea of a vector headed in a certain direction. Now, but it's the relationship between those two numbers that gives it its direction. And if we can come up with a couple of other numbers, you see, that have a resulting direction of 20 degrees, any combination of such numbers would work fine. For example, I've calculated that if we use V to be 11,4, that we'll have the same 20-degree direction associated with this vector that is written in component form. All right, now, I'm not trying to get us to calculate the 11,4. Sometimes it'll automatically be given to us. What I'm trying to point out here is that there may be a variety of ways of dealing with this vector that is going at this angle of 20 degrees. We really don't care so much about its magnitude. You know, we don't care about that. We can use as a relationship with our u vector a vector that has any magnitude along that 20-degree angle, because our formula is going to allow us to make the calculation of magnitude along this vector associated with the u vector. You see, the object is traveling at 50 feet per second in this direction, but all we're trying to find out is how fast it's traveling in this direction. And we can use as a reference any value or any kind of notation for V. We don't care what its magnitude is. We're going to project this onto that, and it's just going to go a certain distance along that angle. You see, that's the idea. Okay, so here's the formula. The projection of U onto V, the notation is this. The projection of U onto V, you see, is, now just kind of look at the formula. It's a dot product of U and V in the numerator. It's the square of the magnitude of V in the denominator, and we're multiplying times V. Now what's so important here to realize is that this is a scalar quantity. Now that means it's one real number to describe the value that comes out of this. And I should have emphasized that a little bit more when we talked about dot product initially, that when we calculate a dot product, we get one real number. You see, we get a scalar quantity, even though it's the dot product of two vectors. We get a scalar as the result. And this turns out to be a scalar as well, because it's simply the magnitude. Okay, so we have a scalar times a vector V here. All right, let's see what happens. We have the dot product of U and V. Now remember, U was the 25 for the horizontal component, 25 root 3 for the vertical component. So it's 25 times 11. Now the 11 comes from here. So it's 25 times 11 plus 25 root 3 times 4. I'm just using 11,4, but it's just for reference. I could use another combination of numbers here that would project me or become a vector along that 20-degree angle. Okay, so that's the idea. All right, now the magnitude of V, again we're using V as 11,4, so it's the square root of 11 squared plus 4 squared, and all of that is squared. Well, the squaring takes out the radical here, so it's simply 11 squared plus 4 squared in the denominator. But making the calculation here, we find this to be about 3.27. Now, that's 3.27 as a scalar multiple of the 11,4. Okay, and then we multiply 3.27 times 11,4, we find this to be 3613. Now, it's important for us to realize that had we used another combination of values here for V, any combination of values that would cause us to have a vector along a 20-degree angle would work fine here. It's just that what will change in this calculation is this scalar right here, the scalar multiple of the vector. You change the vector, the scalar multiple will change, the result will be exactly the same as we have here. All right, that's the important thing. Now, so this is the vector, which is the projection of u onto v. And all we want, though, is the speed associated with that object along that angle. We want the magnitude of this. So we find its magnitude by making a calculation like this. Now, I've designated it as the r is a magnitude. The magnitude along that 20-degree angle for this vector is the square root of 36 squared plus 13 squared, which turns out to be approximately 38.3 feet per second. So that object that is initially projected at 50 feet per second on an angle of 60 degrees is traveling at 38.3 feet per second on an angle of 20 degrees. Take a look at this pattern. Suppose we start with a vector u, which in component form is 3, 5. If we think about the horizontal component 3 in a component form as a vector, it could be written as the horizontal component is 3, 0 in component form, and the vertical component from up here could be written as 0, 5. So we have kind of two different vectors, a horizontal vector and a vertical vector, which together give us u. That is, u is h plus v. So we're kind of separating u into horizontal and vertical components that are vectors, orthogonal components then of u. And we understand that this kind of works out because after all, h is 3, 0, v is 0, 5. Adding those two, we get 3, 5 as expected. Now, this is a rather interesting setup here to kind of break down a vector into orthogonal components. But those orthogonal components need not be horizontal and vertical components. They can have different angles associated with them. Consider this problem. Suppose I have u is 3, 5 and v is 7, 2, and I want to project u onto v. Now, we know how to do that from previously. The projection of u onto v goes with this formula. It's the dot product of u and v over the magnitude of v squared, all times v. Well, let's see. The dot product of u and v, we would have 3 times 7 plus 5 times 2. And then the magnitude of v is the square root of 7 squared plus 2 squared. And now we want to square that. I forgot that part of it, and away we go. So dealing with this, simplifying here, we get, let's see, 21 plus 10, oh, that's 31, and then in the denominator, 49 plus 4, that's 53. When we square the radical goes out, so we have 53. Then 31 over 53 times these two guys gives us these two fractions, which are approximated by 4.1 and 1.17. Now, notice that I have the notation I've used here for the projection of u onto v. I'm saying, gee, we're going to get a vector out of this. It's a vector along the vector of v, but I'm just letting u subscript 1 stand in for that rather than rewrite this again and again and again. Now here's the kicker. We talked about the idea of sort of subdividing a vector into horizontal and vertical components that are themselves vectors. Now what we want to do is think about the vector which is orthogonal with w sub 1, you see, which together with w sub 1 would give u. That is, we want to subdivide u into orthogonal vectors, one of which is w sub 1. Now, it turns out that that's not difficult to do. That if such a thing exists, and it does, then u is equal to w sub 1 plus w sub 2. You see, and that's all there is to it. The sum of those two vectors, orthogonal with one another, is going to give u. And so, using a little algebra on this, subtracting w sub 1 on both sides, w sub 2 is just the difference of those two. And that's all there is to it. So w sub 2 then is u minus the w sub 1 that we found over here from the projection. And subtracting here, we find W sub 2 to be negative 1.1, 3.83. Now let's understand from a sort of a geometric point of view what we have accomplished here, what we're doing. We start with the vector u. Now u was 3, 5, so we go 3, 5. All right. And v was 7, 2, so 7, 2. Now we are projecting u onto v. Okay, we're projecting u onto v. And it produces a new vector, but along that angle, you see, along that dotted line. All right, and it might go beyond here, or it might be over here. We don't know, but it's the projection. And we calculated that projection as W sub 2. We found W sub 2 to be, W sub 1. W sub 1 was 4.1, 1.17. So 1, 2, 3, 4.1, 1.17. And so this is W sub 1. And then we calculated the vector orthogonal with W sub 1, which together with W sub 1 would give u. And we calculated that to be negative 1.1, 3.83. Negative 1.1, 3.83. About right here. So these then are orthogonal components for u. Okay, let's go through it again. We have a u here of 4, negative 2 and a v of 10, 2. We want to find the projection of u onto v, and then we want to find the vector component of u, which is orthogonal to v. All right, the projection of u onto v. Well, let's see, using the formula. It's the dot product of u and v. Now that dot product is 4 times 10 plus negative 2 times 2. All right, and then the magnitude of v, the square root of the sum of the squares of the components of v. So it's the square root of 10 squared plus 2 squared, and then in this denominator that magnitude is squared. So I'm doing that. All right, now we simplify a bit, we get 36 over 104. And we brought down the v vector here, so 36 over 104 times 10, 2 gives us 3.5 and 0.7. All right, so we're more than halfway there. The rest of the calculation is pretty simple. So this is the projection of u onto v. And this vector with another one which is orthogonal with this one are components of u. Let's find that other vector. We find it by using this idea that u is W sub 1 plus some unknown W sub 2, subtracting W sub 1 on both sides. We find W sub 2 is u minus W sub 1, or 4 negative 2 minus the components for W sub 1. And making the calculations here, we find W sub 2 to be 0.5 and negative 2.7. Consider this problem. It's one of the classics, and it involves force vectors. It says a 600-pound boat trailer rig is on a ramp inclined at 30 degrees. What force is required to keep the boat from rolling down the ramp? There are actually two ways to solve the problem, and we're going to look at both of those ways. But let's just understand the forces that are in play here. And if we understand those forces, then we can set up a little right triangulation that will allow us to solve the problem rather easily, it turns out. Now, a weight of 600 pounds means we have a force that is pulling toward the center of the earth. So from the standpoint of where this rig is sitting, we have a force that's coming straight down, and that force is 600 pounds. Now, there's another force in play here to prevent the rig from falling to the center of the earth, and that is the force that is exerted upward by the ramp. You see, and that force is in this direction. All right. Now, it's as though those are components, and the resultant is the force that represents the tendency of the boat to roll down the ramp. And that's really what we're looking for here. So we're looking for the length of this side of that triangle. That's the idea. And we have a little right triangle in here, but we have another right triangle, and that's this right triangle. We kind of need them both. We need this big one to identify the size of that angle, because here we have a 30-degree angle. So the angle inside the little triangle is 60 degrees. All right, so that angle right there is 60 degrees. All right, and let's see, we have, so from the standpoint of this 60-degree angle, we have adjacent side hypotenuse situation going on. So, that's cosine. So the cosine of 60 degrees is x over 600. X then is 600 cosine 60 degrees. Cosine 60 degrees is 1/2. So half of 600 is 300. It's going to take 300 pounds of force to prevent that rig from rolling down the hill. You see, the force being exerted, the tendency is a 300-pound tendency to roll down the hill. So to prevent it from happening, we'll have to exert a force in this direction of 300 pounds. So that's the notion. Now, another way to approach it is as a projection kind of problem. And we can look at it like this, that we have the rig, and then the rig again is exerting this force, and that force is 600 pounds in this direction. So if we were going to write a vector associated with the force of that rig, it would be, let's see, the horizontal component, you see, would be 0. There's no tendency going this way and this way, just considering the weight of the boat, you see. We don't have a tendency this way, we have a tendency that way. And the vertical tendency or component is negative 600 for that 600 pounds of weight pulling down. All right, now, what we intend to do here is take this vector, this 600 pounds going down here, and I guess I can, well, I want to, let me just write it like this. All right, we're going to take this tendency of 600 pounds downward, and we're going to project it onto the ramp. You see, we're just going to project it up here onto this 30-degree angle. Okay, now, we have direction associated with 0, negative 600 is just down right here. We don't have the angle. We could figure the angle, but gee, wouldn't it be the angle that we kind of expected to be? Certainly it would. Now, we're projecting it onto the ramp. But the ramp, we don't have any, there's no magnitude here, but we don't need a magnitude. We can just kind of think about a unit vector situation. We have cosine 30 degrees, sine 30 degrees. The r can be considered to be 1. You see, just unit vector idea. So we're going to project f onto r, and r is represented like this in component form. So the projection of f onto r is the dot product of f and r over the magnitude of r squared times r. All right, let's see what happens. We've got the dot product of these two. Well, that's 0 times cosine 30 degrees plus negative 600 times sine 30 degrees. That's what I have up here. Now, for the magnitude of r, the magnitude of r, really, we can, if we think about this intuitively, it's pretty simple. And we could just write a number down here very quickly. I went ahead and put some things down here, but really, if we're talking about a unit vector here, then the magnitude of a unit vector is 1. So all we have to do is put 1 squared down here, or simply 1 in this denominator. Now, if we put down the items corresponding with the components here, then it would be, let's see, the square root of cosine 30 degrees squared plus sine 30 degrees squared. But what does this mean? This means cosine squared 30 plus sine squared 30. Cosine squared theta plus sine squared theta, oh, that's equal to 1, the basic Pythagorean identity, remember. So this is 1. Square root of 1 is 1. 1 squared is 1. So 1 appears in this denominator. This term upstairs goes out. We have sine 30 degrees times negative 600, and that turns out to be negative 300. Now, notice I brought down the information about r because the formula is requesting it. But remember, this is the unit vector idea. And so this is simply the magnitude associated with this expression. And it's magnitude that we want. So in this projection idea, we are projecting this force of 600 onto the ramp. And so the tendency of the boat to roll down the ramp is a force of negative 300. And therefore, it would logically require a force of 300 pounds to prevent it from sliding or rolling down the ramp. Work is accomplished when a force is applied and an object moves. And the amount of work can be calculated as multiplying the force times the distance. That is, consider this problem. 50 pounds of vertical force on a rope lifts an object 30 feet. How much work is accomplished? Well, we're using this formula, work is force times distance, or F times D. Here the amount of force is 50 pounds, the distance the object moves is 30 feet, 50 times 30, 1500. Notice the unit of measure here, we have pounds and feet. Pounds, feet, foot, pound. Foot pounds is the unit for measuring work. Now the idea of just multiplying force times distance works out really well as long as the force applied is in the same direction as the movement of the object. And that's the case in the first problem, and it's the case in this one as well. A football player uses 200 pounds of horizontal force to move a blocking sled 40 feet. Now let's think about that direction of motion here. So the 200 pounds of force is being applied horizontally, you see, in the same direction as the movement of the blocking sled. The movement of the blocking sled is also horizontal. So we can just directly apply our work formula. Work is force times distance. The force is 200 pounds. The distance is 40 feet. 200 times 40, 8,000. 8,000 foot-pounds of work is accomplished. Now let's consider a situation where the force is not in the direction of the movement of the object. Let us suppose we have a wagon here, and the force applied on the handle of the wagon is 50 pounds, and the angle here between the horizontal and this handle is 60 degrees. Now the movement of the wagon, let's say the wagon moves 12 feet. Now how much work is accomplished? Well, it's a similar idea to the notion of force times distance, but it's the idea that we want the force along this line. We want horizontal force. We want the force along the same direction as the movement of the object, you see. So we want a resultant force times distance. Now, what about this resulting force? You see, it's the resultant force right here, and we have a right triangle situation. And from the perspective of this 60-degree angle, we're talking about adjacent side and hypotenuse. So the cosine of 60 degrees is F over 50. Cosine 60 degrees is F over 50. F then is 50 cosine 60. Cosine of 60 degrees is 1/2. So the amount of force is 25 pounds. So the amount of force, you see, along this, in this horizontal configuration is 25 pounds. And now the idea is work is 25 times 12, or 300 foot-pounds. Now the situation can be sort of summarized like this. It's often the case that we have a force applied in a direction different than the movement of the object. And we can kind of put the ideas together like this, that the resultant force up here, from right up here, was calculated as well, let me generalize it here. It was 50 cosine 60, but it was the force applied at an angle at the cosine of some angle, you see, and then times distance. Well, a lot of times these three factors are written as F times D, force times distance, times the cosine of the angle. Okay, so let's use this idea then and work another problem. Now do understand though that this works even if the force and the movement of the object are in the same direction, because if they're in the same direction, now theta is the angle between the force, the direction of the force, and the direction of the movement of the object. And if that angle is simply 0, we have the cosine of 0, which is 1. You see, so we're back to our original formula. So that would be no big deal. We can use this then in all cases. Consider this problem. A tractor pulls a log 2,500 feet. Tension in the cable is 3,600 pounds. That's the force. How much work is done if the force is applied at 35 degrees above horizontal? Well, we just apply the different information from our problem. We have a force of 3,600 pounds. That's the tension in the cable. We have a distance of 2,500 feet. And the angle, you see, at which this cable is attached to the log, you see, and the motion idea is 35 degrees. So we have 3,600, 2,500 cosine 35 degrees, and this is approximately 7,372,368.4 foot-pounds of work that's